Well, I hoped you enjoyed your day off. It certainly wasn't planned, but actually I needed the break as well. I apologize for the acoustics. I'm in my old house where it's nice and quiet, but a little bit echoey, but hopefully you can still hear me. And so we'll get started here in a whole new chapter, Chapter 4, discussing, oh, hold on one second. Pardon that interruption, but we'll be starting Chapter 4, discussing two new types of functions, one called an exponential, one called a logarithm. But we'll discuss the exponential first because the logarithm just comes from that. So here are our objectives. We'll look at evaluating exponential functions, taking a look at their graphs, working with a base e. We'll see where that comes from. And then compound interest formulas. So we'll see several types of applications for these exponential functions. And if you've ever heard or read in a magazine or a book, you've heard a description that says maybe something grows exponentially, or something has an exponential growth, then they're referring to this exponential function that we'll look at that has several different characteristics, but it actually is a function that rises very fast, or actually it decreases quite fast. Anyway, so let's see what we've seen. We've seen these quadratics, the x squared as a polynomial. We've seen x squared minus 3x squared, x cubed minus 3x squared. Anyway, what I'm trying to get at here is that the exponent is a constant. An exponent of 2, exponent of 3, exponent of 2. In an exponential function, the exponent is now going to be a variable. The base is going to be a constant. So instead of x squared, we'll see 2 to the x, where 2 is the base, x is the exponent. And it's going to be a whole different type of graph that's going to go with this type of function. Always have to have a base. The base is the part that's raised to a power. So here is the base of 3/4. Here is our exponent of a variable x. Because of that change, we have, in our definition, we have to take into account some certain conditions. The exponential function with base a is defined, you know what, I have a typo. It shouldn't say base a right there. The exponential function of base b. That's my old notes. Okay, so the exponential function of base b is defined for all real numbers. It means the domain is all real numbers, where f of x is equal to b to the x power, or y equal b to the x. Remember, f of x and y are interchangeable. So we can write the exponential function in either one of these formats, but we have a restriction. We just have some things to take into account on the base b that we're working with. The base has to be greater than 0. We're not going to work with a negative base. And the base has to be a number other than 1. The base can be anything. It has to be greater than 0, and it can't be 1. Let's take a look at why these below are not exponential functions. F of x equal 1 to the x power. If you were to graph this, this would be a horizontal line. It's the trivial case of an exponential function. That's why we say the base can't be 1. This isn't an exponential function because the exponent is a 2. For it to be exponential, the exponent must be a variable. This won't be an exponential function even though it has a variable for the exponent. The base is a number that's less than 0. The base has to be greater than 0. That's the problem. And finally, x to the x, well, the base has to be a number, a constant, not a variable. So that's why this one's not an exponential function. Well, we've seen what's not. We've seen the basic definition. Let's pull out our calculator because we'll do a lot of calculator work to make to determine some of these values. So pull out the calculator, and we're just going to raise 3 to the, looks like 2.4 power. So pull out your calculator and take your 3, use the caret button to raise it to a power, and hit 2.4. Press enter, and we will get 13.966. So 3 to the 2.4 power. Let's try 5 to the square root of 3 power. Type in a 5, type in your caret, type in your square root, and let's put a 3. So 5 raised to the square root of 3 power. 16.2424. Well, let's go to that. 16.2424. And then finally, let's get pi to the negative 3.6. Pull up pi, get your caret, and let's close this in parentheses. It's negative 3.6. And let's close that off. 0.0162. So you'll have to practice on your calculator finding some values up to 3 or 4 decimal places. In this case I put 4, but at least 3 decimal places. Let's consider some characteristics of the exponential function. F of x equal b to the x. The domain for these functions, whether it is the decreasing type or whether it's the increasing type, the domain is all real numbers for both of those. So you don't have to guess. Domain, all real numbers, we're done. Now we will see the decreasing type where something is decaying very rapidly. That's an exponential decay. If something is increasing rapidly, that's called an exponential growth. So this one would be our growth model. This one over here would be our decaying model. Growth, a population may grow at a certain rate, or a population may die off at a certain rate. Just talking about populations, we may see a growth, we may see a decay. The range for both of these in this standard format, if you notice, they're lying above the x-axis, so we're only going to use the values greater than 0. The reason we can't use equal to 0 is this important comment. There is a horizontal asymptote at y equals 0 for all exponential functions. There's a horizontal asymptote here that your graph cannot cross over. Won't show it on your calculator. You need to know it. There's a horizontal asymptote right here. Y equals 0 is a horizontal asymptote for both of them. Now what's going to be the difference as far as what makes one grow, what makes one decay? If the value of b, if your base is a fraction between 0 and 1, you get the decaying model. If your base, your b, is a number bigger than 1, you get the growth model. So a fraction gives you the decaying, a fractional base gives you a decaying model, a number greater than 1 gives you the growing model. We will take these exponential functions and we'll shift them up or down and left or right. I'm going to hone in on the shifting up or down because if you were to take one of these figures and let's say I have to shift it up 3 units. If I took this guy and shifted it up 3 units, it would look like this. But the horizontal asymptote has to be shifted up 3 units as well. So instead of the horizontal asymptote being at 0, it's now up at 3. Important thing, you have to shift the horizontal asymptote up or down when there's a shift up or down indicated in the function. Lots of students forget that. Shift that horizontal asymptote. So let's work on completing a table of values and checking out some of these shapes. Let's get an x and a y up here, and let me just pick some values for you. I'll pick some x's, you work on the y's. I'll do the same thing over here. If I plug these values, -3, in place for x, I get 2 to the -3. You've got to remember how negative exponents work. you have to take the reciprocal to make a negative exponent positive. So that's actually a 1 over 2 to the positive 3 power, which is 1 over 8. So negative exponents, we take reciprocals. If I place a negative 2 in that function for x, I get 2 to the negative 2, which when I take my reciprocal, I'll get 1 over 2 squared, which is 1 over 4. If I plug in a negative 1, 2 to the negative 1 power will end up being 1/2. Here, 2 to the 0 power is 1. That's a definition. Anything to the 0 power is 1. 2 to the first power is 2. 2 to the second power is not 3. Let's try 4. And 2 to the third power is 8. That's how we can get a table of values and then plot those on our system. But we've got to remember, before I start plotting points, this figure has a horizontal asymptote here on the y-axis. So does this next guy. It's something you can't forget. You got to mark it, horizontal asymptote. The graph is going to approach it, so let's see how the graph is going to approach it based on these points. So I've got 0 and 1. So let's say there's my 0, 1 point. I've got 1, 2. 1, 2. I've got 2 going up to 4. And let's say I've got 3 going up here to 8. Left side, I've got negative 1 is at a half. Negative 2 is at a fourth. Negative 3 is at an eighth. Notice these values are getting smaller and smaller and smaller. It's getting close to that asymptote, but it'll never touch it. So when we connect the dots here, this is the basic exponential shape, exponential growth shape that we'll see. Approaching the asymptote, and then our points are forming this curve. That's our exponential curve, and that's the growth model. Let's look over here and complete these ordered pairs. I put in a negative 3, I get a 1/3 to the negative 3 power. Well, I've got to flip it. So if I take the reciprocal, that's 3 over 1 to the positive 3 power. And 3 times 3 times 3 is 27. Let's do that again. 1/3 to the negative 2 power means I have to flip it. Okay, so let's do this one. 1/3 to the negative 2. To get rid of the negative exponent, I have to take the reciprocal and raise it to the positive 2 power. The reciprocal makes the negative exponent positive, so I get 9. 1/3 to the negative 1 means to take the reciprocal and raise it to the positive 1. Let's do these. 1/3 to the 0 is 1. Anything to the 0 is 1. 1/3 to the first is 1/3. 1/3 to the second is 1/9. And you get the picture. This is going to be 1 over 27. Now that we have the horizontal asymptote marked, let's just go ahead and plot these points. So I just kind of always start off at the 0, 1 mark. There's 0, 1. 1 is down at 1/3. So we'll say 1 is down here at 1/3. 2 is at a 9th, even smaller than that. 3 is at 1 over 27, even smaller than that. Now look at the points. They're getting close to the asymptote, but they will not touch it. Negative 1 goes up to 3. Negative 2 goes up to 9. And the other one goes way up here to 27. And when I connect the dots, I will see the curve, that exponential curve, approaching the asymptote, but not crossing over it. And as I go left to right, since it's decreasing, this is the decay version of the exponential function. And we can plug those in our calculators and do some tracing and find those values as well. Let's look at transformations. Let's take the basic shape and transform it, and when we transform it or translate it, we'll have to shift the horizontal asymptote up or down if an up or down shift is indicated. Oops, where did that go? Here it is. So here's the basic exponential, but what we've done is we put a subtraction of 3, which means it gets shifted down 3 units. So if my horizontal asymptote is normally at 0, I've got to shift it down 3 units here at -3. So you've got to mark that. This one is indicating a shift that goes up 2. So my horizontal asymptote is going to be here up 2. Up or down shifts have to will indicate that your horizontal asymptote must be shifted up or down accordingly. Now we can throw this in our calculator and show we'll get the 2 to the x that we did earlier, and it's just going to be shifted down 3 units. Now this point up here was 0, 1. If I take that 0, 1 point and shift it down 3 units, it's going to be down here at 0, -2. So that intercept shifts as well, and so it'll be down here at 0, -2. We'll pull out the calculator and graph 2 to the x minus 3. Let's clear that out and go 2 to the x minus 3 using the caret. And we can graph that. Ooh, not sure what window I was in last time, so I probably ought to do, let me go to zoom 6. There we go. We kind of see it scooching along, and then it starts to do its increase. Now what your calculator doesn't show you is that there is a horizontal asymptote here at the number 3, and you can see if you hit the trace button, your y-intercept there is at 0, -2. It doesn't show you, but you need to know your asymptote is at 3. And so it shows us our curve just doing this. Basic shape of that exponential function. Let's check this one out, put it in our calculator, and verify the results. Where did my calculator go? So this one is a -3 to the x plus 2. Let's type that one in. Okay, -3 raised to the x plus 2. Make sure I've got that typed in right. Yep, -3 to the x plus 2. And let's go ahead and graph that. The negative in front caused it to reflect across the x-axis, and the plus 2 caused it to move up 2 units. So I'm going to have my horizontal asymptote up here at the number 2. So my horizontal asymptote is up here at 2. If you go back to the graph, you'll notice how your graph was flipped over and it did something like this. Pull it back up. Yeah, that's how the graph worked. So that's just the basic shape from our calculator of what the graph should look like. Let's do domain, range, and asymptote. Don't ever stop to think about these. Domain will always be set of real numbers. Now the range depends on where that asymptote is and if the graph is above or below the asymptote. Here the asymptote was at -3 and the graph is everything above the -3. So the range is everything greater than -3. No equal to, because it's an asymptote, but it's everything greater than -3. The range over here, well, here's the asymptote and the graph is all, in this case, is all below the asymptote. So if I want to figure out my range, it starts at negative infinity and stops up here at that asymptote of 2. So we could say y less than 2 as our range. And the horizontal asymptote is at 3 and at 2. Notice those values will always coincide. Look to see where your graph is placed.